So the first speaker is Jack. He's a Wesley. He's an visiting assistant professor at UC San Diego, and he's going to be talking about book Ramsey numbers.
All right,
please.
Thank you, and thank you very much, Curtis, for the invitation. It's nice to be up here in Canada. So I know it's a discrete math conference, and
oh, you might have to hit the. Yeah, that's not hooked up to it, but you have a.
I'll just do this. All right. So yes, I know many of you are already familiar with all of this, of course, but the sort of classical example in Ramsey theory is that if you take any 6 people, then at say a party, then you necessarily will have either a group of 3 mutual friends or a group of 3 mutual strangers. And phrased in graph theoretic terms, if I take the edges of K6, color them each red and blue, then I will necessarily get either a red monochromatic triangle or a blue triangle. And the more general statement here is Ramsey's theorem from about 100 years ago, that if you give me any parameters R and S, then there's some n where if I two-color the edges of a large enough Kn, then that coloring will give me either a red copy of Kr, so a red click, or a blue copy of Ks. And we are very interested in computing this Ramsey number, R of Rs, which is defined to be the smallest such n. So the threshold where we are guaranteed to find this pattern no matter what. And as many of you probably know, these things are very, very hard. This is a very innocent looking problem, but actually finding these numbers is not easy at all. And this is essentially all we know in terms of exact values. We know up to R39 and up to R45, but no tight bounds for any of the other cases. And of course, there's this famous quote by Paul Erdős, which says that if aliens were to invade Earth and say, tell us the value of Ramsey 5, or we will destroy you, then Erdős says that as long as the NSF money gets turned back on, then we could all come together within a year and compute this number R55. But if they instead ask for R66, then it is totally hopeless. We are screwed. Instead, we should just put everything into the military, and we should try to destroy the aliens first instead. So this is a very difficult problem. And it's a very interesting problem, both in the asymptotics and trying to pin down these exact, precise values. Okay, and the difficult part here generally comes from the upper bounds. The search space is very, very large, and we need to rule out, a huge number of possibilities for these graphs, and these often involve these massive computations. So if you want a job next fall, you might want to make this problem a little bit more tractable. And instead of looking for these classical Ramsey numbers for clicks, Kr and Ks, we can ask the same question for arbitrary graphs, G1 and G2. So the Ramsey number R of G1, G2, I'm asking for the smallest n, where every red-blue coloring of Kn has either a red G1 or a blue G2. And you can take this a step farther and do this for more than 2 colors. So if there are more than 2 graphs, then it just means more colors. But what's nice here is that when you look at other families of graphs besides the clicks, you get a much nicer behavior. And these are just sort of 2 randomly chosen examples, but for C3, Cn, for instance, you have a nice, easy, closed formula, 2n minus 1. And for paths, Pm, Pn, you get another nice, essentially linear thing. And I think n is bigger than m here. But it doesn't matter. The point is that there's nice examples, nice formulas. And there's this very beautiful, nice dynamic survey, which has sort of cataloged tons and tons of these numbers for the past 30 years. And this is hundreds of pages long and has a very nice resource for these types of results. Okay, so we're going to look at a different family graphs, which you might have guessed from the title, are the book graphs. So if you haven't seen this before, it's a fairly simple graph, Bn. I have sort of a spine of the book, and I have n triangular pages of the book. So this is B3 and B4. So the first sort of study of these numbers came about 50 years ago from Rousseau and Sheehan. And in their paper, they have this following quote, where they say that the book Bn is not quite the same status in graph theory as complete graphs, paths, cycles, or wheels. But I think they're being perhaps a little too modest. Very recently, there's been a lot of interest in the asymptotics of these book graphs, and there's been a lot of nice results and characterizations of some of the extremal colorings in an asymptotic sense. And there's this recent breakthrough on the asymptotics of the diagonal Ramsey numbers, and something called the book algorithm plays a key role in this proof. That got it from 4 to the s to something smaller than 4 to the s. So the point is that books are interesting, I hope. All right, so what did they prove in this paper? So they proved a lot of things, but I want to focus on these few results. So they looked at these sort of diagonal Bn numbers, or these sort of almost diagonal Bn minus 1 Bn and Bn minus 2 Bn. And here they actually got the upper bounds, some good upper bounds here. And they're roughly 4n with some constant factor, additive constant there. And they have an exact value for this infinite family for this diagonal case, Bn, Bn. So we know that it's exactly 4n plus 2. We have this expression q when this is a prime power. But they just gave these upper bounds, these roughly 4n upper bounds, and they didn't say much about the lower bounds for these other cases. And I'm not going to talk too much about the upper bounds, but Goodman's theorem, which tells about the number of monochromatic triangles in a graph, the upper bounds come from a very careful analysis of how you get this. But in this first case, where they actually get this tight bound here, this comes from the Paley graphs. And this is why you need this 4n plus 1, if you're familiar with this. Okay, so looking at this table of what we knew about book Ramsey numbers, I decided to see what we could do. And we got this following result. So before we had this, Rousseau and Sheehan had this exact value for Bn, Bn, and I was able to generalize it to a similar looking result for this off-diagonal case, Bn minus 1, Bn. So it gives us an infinite family of these numbers when I have these 1 mod 4 prime powers for this expression q. But more than that, I, along with another group, which Gwen McKinley is talking about in a few days, I believe, if you're interested in that, we sort of independently came up with some new computational lower bounds for these as well, and some exact values. So before all of this, this was known only for n up to about 4 or 5, but we pushed it out to around n equals 20. So we have some exact values for modest-sized n and this infinite family in this bn-1 case. And beyond this sort of almost diagonal case, we looked at some other small values as well. And we've tightened many of these bounds in this these B2 cases, and this exact one for B3, B7 as well. And more recent result from a few months ago was that these same methods, which I will talk about in a moment, they can be done for some multicolor graphs, some 3-color Ramsey numbers involving cycles. So we have exact values now for this C3, C6, C6, and C5, C6, C6. And this was sort of a conspicuous gap in the table that is known. And at the very end, we get a slight improvement on this other. But even if you don't care, about these what these values actually are, the point is these methods will give us some nice tighter bounds than what was known before. Okay, so as Curtis mentioned, and if you know me, I very much love SAT solvers, and these things have been used with great success in both graph and arithmetic Ramsey theory, including this notoriously large proof, 2-petabyte proof of sure number 5. But I want to focus here on the graph results. So SAT solvers have played some important role in many of these recent results. So this first one is R334. This is only the second known 3-color classical Ramsey number, and that was shown to be 30. We've gotten many other sort of diagonal results for sparse G. And this third result is about certifying that this Ramsey number is correct. So a lot of these older results come from massive computations, lots and lots of cases to check. That it's very difficult for a human to actually verify. So Curtis and his co-authors were able to certify that this upper bound for R38 is indeed correct using SAT methods. And then finally, this infamous R55 problem, the upper bound was cut down recently from 48 to 46, and SAT played a nice role in some of the case checking for that as well. And this entire proof, this R55 proof, took about 80 years of CPU time to verify. So it's very, very much a lot. All right, so the results of mine that I just showed, most of these were obtained via this SAT solver KISAT. This is a state-of-the-art SAT solver. It has many accolades, won many of these SAT competitions, designed by Armin Bier. And this is a very good general purpose solver. But the solve times are not so outrageous. They're not, on the order of years and years of CPU time. But instead, some of these are very, very fast, just a few minutes, and they could take up to a few days on a single machine. And then we want, of course, as I mentioned before, we want all of these results to be certified in some way. SAT solver, very complicated piece of software, has thousands of lines of code. And while they should be trusted in general, people who write them are very good. It's perhaps difficult for a single human to verify that thousands of lines of code are indeed working the way they should. So it's important to have some external method of certifying these things. And this led to this 2-petabyte proof that I mentioned before. So as these times are not quite so enormous, neither are the proof sizes, but these are still fairly non-trivial. The largest proof here for the 60-hour solve is about 100, 200 gigabytes. So it's a non-trivial thing to certify. And then, as long as I have time, I'll talk a little bit about some of these lower bound constructions that give this infinite family of tight bounds. These come from circulant graphs and generalizations, but these were all found essentially using SAT and IP solvers. These provided the inspiration for the general construction. Okay, got about 10 minutes left, so I'll talk a little bit about some of the more technical details of how all of this is put into a computer. So we start, if we want to compute this number R of G1, G2, now we need some way of translating it into, we need some way of translating this problem into a Boolean formula. So here it is fairly straightforward, but we have a variable, call it xe for each edge. You want to set this variable to true exactly when we color this edge red. So if this variable is true, it's red. If it's false, it's blue. And then we just want to forbid each of these subgraphs, G1, G2, in the appropriate color. And then we can introduce a clause, just a or of these variables that forbid this. So you have a clause for each of these first ones. G1, you or together every edge in each subgraph of that form. So you take this or of all of the xe's, and that tells me that at least one of them must be a blue edge. So there can't be a red G1. And then similarly, the same thing, we do it for G2 and say that one edge in each subgraph must be red. And then if this, you get this huge formula where if it is satisfiable, we get a lower bound for this Ramsey number. And if it's unsatisfiable, then we get an upper bound. And this is the general procedure that we need to encode this problem in this form. And then we can throw in some additional constraints of the problem. This can, for example, be if we're looking for a graph of a certain type for a lower bound, we can enforce that a graph must be circulant or have some other sort of symmetries in some way. Or in some cases, we can implement other sort of SAT techniques to encode cardinality, numbers of edges, etc. And then the next step is to break these symmetries. And there's a very nice tool called Shatter, which can do this all automatically for you. And this will take things from being totally intractable to doable in some cases. And then I won't talk too much about the details of the rest of it, but there are other techniques. One thing is called cube and conquer, which can enable all of this to be parallelized. And then you feed this all to a solver, cassette, for example, and then at the end, you want to certify that everything was done correctly. Again, I don't have time to talk about those details, but happy to chat. Okay, so this is the sort of general process for computing these upper bounds. Most of these were just fed into the solver, and after implementing all of this carefully, you just run it and hope it works, and it did for these cases. But the other side of this is trying to find these lower bounds, where we actually want sort of explicit graphs, explicit colorings of graphs that give us lower bounds that avoid the given G1 and G2. So a sort of hint of where to search is to look at circulant graphs. So a circulant graph is a graph where if we take all the n vertices of this graph, put them around in a circle, then we find this set S of distances where we connect them. We connect vertices only if and only if their distance mod n lies in this given set. I'll show an example. So these Paley graphs, which I mentioned before, you connect everything that is a quadratic residue mod n apart. So this is for 13 vertices. And this set S is a set of quadratic residues, mod 13. And we connect everything that's 1 apart. See this outside circle there, 4 apart, 9 apart, etc. And the point here is that circulant graphs actually give us a lot of the bounds for the classical Ramsey numbers, as well as some nice little drawings. So these 4 graphs are on 5, 8, 13, and 17 vertices. And these give us tight lower bounds for some of these small classical Ramsey numbers. But unfortunately, this is sort of where it stops. You can't keep going with this forever. They're not tight anymore. But we can look at generalizations of these circulant graphs in hopes of finding some nicer things. So just to make one definition, details are not so important. But essentially, we want to generalize this into something called a block circulant graph. So a circulant matrix is essentially the adjacency matrix of a circulant graph. And a block circulant graph is a graph whose adjacency matrix has all of these blocks, where each block is itself a circulant matrix. So it's a direct generalization of a circulant graph. And these were used with tremendous success for these Ramsey numbers for clicks, and then clicks minus an edge. And this got some very dramatic, very nice improvements on these R of KR, KS minus an edge. And in these 2 papers, a lot of these lower bounds used these 2-block circulant Ramsey graphs. And this main result that I mentioned before, this tight, yes. Yes, I didn't say that, but yes, I mean here K equals 2, so a 2 by 2 blocks essentially. Yes. And what we showed this paper is that essentially a 2-block version of a Paley graph, direct generalization, will give us this almost diagonal tight lower bound in this case. But the details take a little bit to check. All right, so this is sort of only the beginning. There are a lot of other different directions that can be taken with this, and I think there's a lot of room for improvement using both SAT and some of these circulant constructions. One very natural generalization, and this is not a new thing, this has been done before elsewhere, but I can do this for Cayley graphs rather than circulant graphs, where you fix some group G and you connect edges that are a certain distance apart in the Cayley graph. And then a lot has been done with local search methods, simulated annealing, and so forth. And this has gotten a lot of nice lower bounds as well. So I think there's a lot of opportunity to do this local search, but with some of these additional restrictions, either for block circulant or block Cayley graphs. And a lot can be done with SAT as well. There's a lot of ways to extend these techniques and doing some so-called dynamic symmetry breaking and doing some symmetry breaking essentially while the solving is going on and pruning a lot of the search space that way. And there's a lot of recent interest with finite geometry to get some nice constructions there. And as well as a whole host of other coloring problems in discrete math that can, I believe, benefit from SAT. So that's it. Thank you.